Welcome to the deep dive. We're kicking things off today with, well, a pretty famous story about our early attempts to picture the universe. It's almost funny now, but it really sets the scene.
Ah, you mean the one from A Briefer History of Time, The Old Lady and the Turtles.
Exactly that one. The scientist gives a talk, and this woman stands up saying, basically, nice try, but the world's a flat plate on a giant turtle.
And when he asks what the turtle's standing on,
She just says, you're clever, young man, very clever. But it's turtles all the way down.
hey, yeah, it's a perfect little parable, isn't it? About models that don't actually solve anything fundamental.
Which is kind of the opposite of what we're doing today. Our mission here is a deep dive into how our picture of the universe really evolved from, maybe not literal turtles, but certainly from early ideas right up to the edge of what we know now.
Exactly. We're digging into the big questions the source tackles. What do we genuinely know? Where did this universe come from? And a big one, where's it all headed?
So that story starts way back, trying to figure out the basics. Like, are we on a flat thing or a round thing? The flat Earth idea stuck around for a surprisingly long time.
It did, even though the ancient Greeks, specifically Aristotle around 340 BC, had already made some really solid arguments for a spherical Earth.
Based on observation, right? Like lunar eclipses.
Precisely. He pointed out that the Earth's shadow on the moon during an eclipse is always round. A flat disk could cast an oval shadow or a line, depending on the angle, but only a sphere always casts a round shadow. Pretty smart.
And the ships coming over the horizon, too. You always see the top of the mast first, then the sails, then the hull.
Yeah, if Earth were flat, you'd just see a tiny dot get bigger and bigger. Simple observations, but very powerful logic.
Okay, so we figured out it's a sphere, but we still thought we were the center of everything for a long, long time.
Oh, absolutely. That was the Ptolemaic model from Claudius Ptolemy in the 2nd century AD, Earth-centered, geocentric. And to make it work with how the planets seemed to wander across the sky, well, it got complicated.
That's where the epicycles come in, the circles on circles.
Exactly. Tiny circles whose centers moved along bigger circles. It sort of matched the observations mathematically, but it had this glaring flaw.
Which was?
It predicted that the moon, because of its complex path in this model, should sometimes look twice as big as other times.
And obviously, it doesn't. You just have to look up.
Right. It was a major observational failure. That model, despite being accepted for centuries, even by the church, was fundamentally wrong.
Until Copernicus came along in the 1500s and said, hang on, what if? What if the sun is at the center?
A much simpler idea, wasn't it? Though it took Kepler adding that the orbits weren't perfect circles but ellipses to really make it fit the data accurately.
And that shift, sun-centered elliptical orbits,
Yeah.
that really paved the way for Isaac Newton, didn't it?
It absolutely did. Set the stage completely.
Okay, let's talk about Newton then. Because his work wasn't just about what he discovered, but how. It sort of defined what a scientific theory even is.
That's a crucial point. A scientific theory isn't just an idea. It's a model of the universe, or some part of it, plus a set of rules. Rules that link quantities in the model to things we can actually observe and measure.
And a good theory.
A good theory needs two things. One, it should accurately describe a whole bunch of observations without needing loads of sort of arbitrary tweaks or special conditions. Elegance, you might say.
Okay. And two.
It has to make definite predictions about the results of future observations. Predictions that could, in principle, prove the theory wrong. If you can't test it, if you can't potentially falsify it, it's not really science in the modern sense. Newton's gravity was a perfect example of this.
Before Newton, though, we had Aristotle's ideas dominating. That things naturally want to be at rest and heavier things fall faster.
Right. And Galileo really challenged that. His experiments, like rolling balls down inclined planes, showed something quite different.
He found that if you ignore air resistance, everything accelerates downwards at the same rate. Didn't matter how heavy it was.
Exactly. That was a key insight. And Newton built on that with his universal law of gravitation.
Which states? Remind us.
That every object in the universe attracts every other object with a force. A force that's proportional to the product of their masses, multiply their masses together, and inversely proportional to the square of the distance between them. Get twice as far away, the force drops to a quarter.
Okay, but hang on. If gravity pulls harder on heavier objects, why do they fall at the same rate as lighter ones? That still feels a bit like magic.
It's beautiful, actually. Newton's own laws explain it perfectly. Yes, if an object is twice as heavy, gravity pulls on it with twice the force. But according to Newton's laws of motion, that object also has twice the mass, meaning it has twice the inertia. It's twice as hard to get moving.
Ah, so the extra force is perfectly canceled out by the extra resistance to moving.
Precisely. The twice the force divided by twice the mass gives you exactly the same acceleration as 1 unit of force divided by 1 unit of mass. It just works out for everything.
Yeah. It's neat. Very neat. But Newton's work also brought up a philosophical headache.
Right.
About space itself.
Yeah, his first law of motion. An object stays at rest or moves in a straight line at constant speed unless acted on by a force. The implication is profound. There's no absolute standard of rest in the universe.
Meaning you can't definitively say whether something is truly moving or truly still, only relative to other things.
Exactly. Think about being on a perfectly smooth train. If you drop a ball, it falls straight down relative to you, just like it would if the train was stopped at the station. There's no experiment you can do inside the train carriage to tell if you're moving at a constant speed or not.
So motion is purely relative.
According to Newton's laws, yes. And this lack of an absolute space, a fixed backdrop for the universe, apparently really bothered Newton himself, but it was baked into his own physics.
And that lack of absoluteness, that sets us up for the next big upheaval, doesn't it? Getting rid of absolute time.
It does. And that story starts with light, with the realization that light doesn't travel instantaneously.
That was Ole Romer in 1676, observing Jupiter's moons.
That's the one. He noticed slight variations in the timing of their eclipses depending on whether Earth was closer to or farther from Jupiter in its orbit. The only explanation was that light took a measurable amount of time to cross that distance. Finite speed.
Okay, fast forward a couple centuries. Maxwell unifies electricity and magnetism.
And his equations predicted that light is an electromagnetic wave, and crucially, that it should always travel at a specific fixed speed. Let's call it c.
Fixed relative to what? If there's no absolute space, no absolute rest frame.
Exactly the problem. People hypothesize this invisible substance, the luminiferous ether, filling all of space as the medium light waves travel through, the fixed frame.
Makes sense. So try and measure our movement through this ether.
Which is what Michelson and Morley tried to do in 1887. They built this incredibly sensitive interferometer to detect the tiny difference in the speed of light expected as the Earth moved through the ether in different directions, like swimming with or against a current.
And they found
Nothing. No difference. The speed of light was exactly the same, no matter which way the Earth was moving, no matter which way they pointed their device. It was a huge shock. The ether apparently didn't exist.
which left physics in a bit of a mess.
A big mess. Until Einstein, 1905, special relativity.
And his big idea was essentially taking the Michelson-Morley result at face value.
Basically, yes. He started with two postulates. One, the laws of science should be the same for all observers who are moving freely, not accelerating. Two, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source.
Okay, if everyone measures the same speed of light, but people are moving relative to each other, how does that work? If I'm on a train and shine a flashlight forward, and someone on the ground measures that light too.
You both have to measure the same speed, but clearly the person on the ground sees the light travel a greater distance in the same amount of, well, their time because the train itself is moved.
So if the speed is the same,
Yeah.
but the distance is different?
The only way to make the maths work, the only thing left that can be different for the two observers, is time itself. Your clocks must tick at different rates.
Wow. So to keep the speed of light constant for everyone, we have to ditch the idea of a single, universal, absolute time.
That's it. Time becomes relative. It depends on your motion. Time dilation. It's not just theory, it's measured. Clocks on fast-moving planes or satellites literally tick slower relative to clocks on the ground.
And special relativity also gave us EMC squared, right?
Yes. Mass and energy are equivalent, which also explains the cosmic speed limit. As you accelerate an object with mass, you pour energy into it. But because energy has mass equivalent, the object's effective mass increases as it gets faster.
So the closer you get to the speed of light.
Its mass heads towards infinity, and you'd need infinite energy to push an infinite mass any faster. So things with mass can approach the speed of light, but never quite reach it. Only massless things like light itself can travel at c.
Okay, that's special relativity. But Einstein wasn't done. 10 years later, 1915, general relativity.
Right. GR was his theory of gravity. And it was even more radical. Gravity, he said, isn't a force pulling things across space.
It's the shape of space, or space-time.
Exactly. Mass and energy warp the geometry of space-time around them. Think of putting a bowling ball on a stretched rubber sheet. It creates a dip.
And if you roll a marble nearby.
It tries to go in a straight line, but the curve in the sheet guides its path, making it orbit the bowling ball. Objects in space aren't being pulled. They're following the straightest possible path called a geodesic through curved space-time.
That's a mind-bending way to think about gravity. Was there immediate proof?
There was. GR perfectly explained a tiny anomaly in the orbit of Mercury that Newton's gravity couldn't quite account for. And then, the big one. In 1919, during a total solar eclipse, Arthur Eddington observed starlight bending as it passed near the sun.
Because the sun's mass was warping space-time.
Precisely. And the amount of bending matched Einstein's predictions perfectly. It made him world-famous overnight.
And GR also affects time, doesn't it? Like special relativity.
It does. Time runs slower in stronger gravitational fields. Closer to a massive object, time literally ticks more slowly relative to somewhere farther away.
Is that significant?
Oh, absolutely essential for modern technology. Think about GPS. The satellites orbiting Earth are in a weaker gravitational field than we are on the surface. Their clocks run slightly faster.
So we didn't correct for that.
Your GPS position would become inaccurate by kilometers within a single day. We have to account for relativistic time dilation, both from their speed, special relativity, and the difference in gravity, general relativity, for the system to work at all.
Okay, so Newton got rid of absolute space. Einstein got rid of absolute time. Then Edwin Hubble came along and kind of got rid of our absolute unique place in the cosmos.
That's a good way to put it. In 1924, Hubble provided definitive evidence that those fuzzy nebulae astronomers saw weren't just gas clouds within our own Milky Way. They were entire other galaxies, island universes, incredibly far away.
Suddenly the universe got a whole lot bigger.
Immensely bigger. Billions of galaxies. Not just one. But his really crucial discovery came from analyzing the light from these distant galaxies.
The redshift.
The redshift. He noticed that the light from almost all of them was shifted towards the red end of the spectrum, like the pitch of an ambulance siren dropping as it moves away from you. The Doppler effect, but for light waves.
Meaning they're all moving away from us.
Yes. And the farther away a galaxy was, the faster it seemed to be moving away. The conclusion was inescapable. The entire universe is expanding.
Wow. And the math actually predicted this before Hubble saw it.
Amazingly, yes. A Russian mathematician, Alexander Friedmann, had already found solutions to Einstein's general relativity equations back in 1922 that described a dynamic, non-static universe. Einstein himself initially didn't like that implication.
So Friedmann's models, they laid out possibilities for the universe's fate based on this expansion.
Right. He showed there were basically three scenarios, depending on how much stuff, mass, and energy there is in the universe, and thus how strong gravity is.
Okay, what are they?
If there's enough mass, gravity would eventually overcome the expansion, slow it down, stop it, and pull everything back together in a big crunch.
Scenario 1, collapse.
Scenario 2. If there's not much mass, gravity isn't strong enough, and the universe expands forever, getting colder and emptier.
Okay, perpetual expansion.
And scenario 3. The critical case. Exactly the right amount of mass so that the expansion slows down forever, approaching zero, but never quite reversing, balancing on a knife edge.
So which one is it? And how do we know this expansion even started from somewhere specific?
Well, the evidence for beginning a hot, dense state came rather unexpectedly in 1965. Penzias and Wilson, two radio astronomers, were trying to eliminate noise from their antenna.
And they kept finding this faint, persistent microwave hiss.
Exactly. Coming equally from all directions in the sky, day and night, season after season. It turned out to be the leftover heat, the afterglow from the Big Bang itself, the cosmic microwave background radiation, or CMB.
Proof that the universe was once incredibly hot and dense and has been cooling as it expands ever since.
A monumental discovery. It perfectly matched the predictions of the Big Bang model.
Okay, so back to the fate question. Collapse or expand forever? Which Friedmann model fits? To know that, we need to know how much stuff is actually in the universe, right? Its density.
Precisely. We need to weigh the universe, essentially. And when we add up all the matter, we can see stars, gas, dust.
It's not enough.
Nowhere near enough. There isn't nearly enough visible matter to provide the gravity needed to eventually halt the expansion, let alone cause a collapse. Based on what we see, it should be scenario 2, expand forever.
Right.
easily.
But
But we see evidence for much more gravity than visible matter can account for. When we look at how stars orbit within galaxies, especially near the edges, they're moving way too fast.
faster than they should be if the galaxy's gravity only came from the stars and gas we see.
Much faster. They should just fly off into space. The only way they can be held in those orbits is if there's a huge amount of extra mass, creating extra gravity that we can't see.
Dark matter.
Dark matter. Some invisible, non-interacting, except via gravity substance that might make up, some estimates say, up to 90% of the total mass in galaxies and galaxy clusters. We know it's there from its gravitational effects, but we still don't know what it is.
Okay, so add in dark matter. Does that give us enough density for the critical model, or even a collapse?
Still probably not quite enough for a collapse, but maybe closer to the critical density needed for scenario 3, the flat universe. And observations of the CMB, its tiny temperature fluctuations, actually suggest the geometry of the universe is flat, or very close to it.
So the universe seems to have exactly the critical density.
Yeah.
But visible matter plus dark matter still don't add up to that critical value.
Correct. There's still something missing. And it gets even weirder.
Oh.
Observations of very distant supernovae, which act as standard candles for measuring cosmic distances, revealed something truly unexpected in the late 1990s. The expansion of the universe isn't slowing down, as you'd expect, due to gravity.
Speeding up.
It's accelerating. Something is actively pushing space apart, overcoming gravity on the largest scales.
What on earth could do that?
We call it dark energy. It seems to be a property of space itself, some kind of vacuum energy or cosmological constant acting like an anti-gravity pressure. It makes up the missing density needed to get us to that critical flat geometry, and it explains the accelerating expansion.
So dark matter providing extra gravity we can't see, dark energy providing anti-gravity we can't see. Most of the universe is invisible and mysterious.
Something like 95% of the total mass energy content of the universe appears to be in these dark forms. We only understand the 5% that's normal matter. It's humbling.
And this accelerating expansion driven by dark energy seems to lock us into the expand forever fate, right? Getting colder and darker.
Based on current evidence, yes. Barring any future surprises about the nature of dark energy changing over time.
Okay, all this expansion points back to a beginning, the Big Bang, which the source describes as a singularity.
Yes, according to general relativity, if you run the expansion backwards, everything converges to a single point around 13.7 billion years ago. A point of infinite density, infinite temperature, infinite space-time curvature, the singularity.
But infinities in physics usually mean the theory is broken down, don't they?
Absolutely. General relativity, our best theory of gravity, predicts its own downfall at the Big Bang singularity. It simply can't describe that initial moment or what, if anything, came before it. Our current laws fail right at the origin point.
We can describe what happens just after, though.
Yes, quite well. Fractions of a second after the Big Bang, it was an incredibly hot, dense soup of elementary particles and radiation. By about 1 second, around 10 billion degrees Celsius, much later, maybe hundreds of thousands or a million years after, it finally cooled enough for electrons to combine with nuclei to form the first stable atoms, mostly hydrogen and helium.
Making the universe transparent to light for the first time, which is what we see as the CMB.
Exactly. And it makes you think, the heavier elements that make up planets and us. Things like carbon, oxygen, iron, even gold.
They weren't made in the Big Bang.
No, they were forged much later inside generations of stars and then scattered across space in supernova explosions. We are, quite literally, made of the ashes of dead stars.
Stardust.
Yeah.
Okay, singularities aren't just at the beginning of the universe. General relativity also predicts them inside black holes.
Right. The idea goes back even further, actually, to Michel and Laplace in the late 1700s. They reasoned that if an object was massive and dense enough, its escape velocity could exceed the speed of light.
So nothing, not even light, could get away. A dark star, or what we now call a black hole.
And GR describes the boundary of no return as the event horizon. Once you cross that, you can't escape. And inside, at the center, GR predicts another singularity.
And the fate of someone falling in. Not pretty.
Not pretty at all. Because gravity gets stronger closer to the singularity, the pull on your feet would be vastly stronger than the pull on your head. Tidal forces would stretch you out like spaghetti.
Spaghettification. Lovely term.
Yeah, vivid, anyway.
So this brings us to the biggest challenge in physics today, doesn't it? These singularities, the breakdown of GR, it points to the clash between our two best theories of the universe.
Precisely. General relativity, which describes gravity and the large-scale structure of the universe beautifully, and quantum mechanics, which describes the other fundamental forces and the behavior of matter at the smallest scales, equally beautifully.
But they don't play nice together. They seem fundamentally incompatible.
Particularly in regimes where both should apply, like the Big Bang singularity or the center of a black hole, where gravity is incredibly strong over incredibly small distances. The mathematics just breaks.
And quantum mechanics itself brought its own philosophical bombshells, like Heisenberg's uncertainty principle.
Right. The idea that you fundamentally cannot know both the precise position and the precise momentum or speed of a particle at the same time. The more accurately you know one, the less accurately you can possibly know the other.
Which destroyed the old deterministic dream, the idea that if you knew everything about the present, you could predict the future perfectly.
It did. If you can't even know the starting state perfectly, prediction becomes inherently probabilistic, not certain. This is where Einstein famously objected, God does not play dice. But quantum mechanics seems to insist that he does, or at least that randomness is fundamental.
So the ultimate goal now is to find a single theory that unites GR and QM, a theory of quantum gravity.
That's the holy grail. To merge gravity with the quantum framework, one major hurdle is dealing with those quantum fluctuations, the virtual particles that the uncertainty principle allows to pop in and out of existence even in empty space.
Why are they a problem?
Because these virtual particles have energy, and according to GR, energy creates gravity. If you calculate the gravitational effect of all these virtual particles, you get infinite energy density, infinite space-time curvature everywhere, which is obviously not right.
So we need a new approach, like string theory.
String theory is one of the leading candidates, yes. It replaces point-like particles with tiny, vibrating, one-dimensional strings. Different vibration modes correspond to different particles, and one mode naturally corresponds to the graviton, the hypothetical quantum particle of gravity.
But string theory comes with its own baggage, right? Like extra dimensions.
It does. For the math to work consistently, string theory typically requires not just the 3 spatial dimensions plus time that we experience, but 10 or 11 or even 26 dimensions in some versions.
Where are they?
The idea is that the extra dimensions are curled up incredibly small, perhaps on the Planck scale, far too tiny for us to perceive directly.
So why do we only experience 3 large spatial dimensions? Is there a reason?
Well, one argument often invoked is the anthropic principle. It basically suggests that the universe must have properties that allow life to develop within it at some point in its history.
And how does that relate to dimensions?
It turns out that if there were more than 3 large spatial dimensions, the laws of gravity would likely make stable planetary orbits impossible. Planets would either spiral into their star or fly off into space.
So no stable orbits, no stable planets, probably no life like us to observe the universe.
Exactly. We observe 3 large spatial dimensions because only in a universe with 3, or perhaps fewer, but 3 seems necessary for complexity, could observers like us evolve to ask the question. It's a bit circular, and some find it unsatisfying, but it's one possible explanation.
Okay, so we've gone from turtles all the way down through Aristotle's sphere, Ptolemy's epicycles, Copernicus and Kepler's orbits, Newton's gravity.
Then Einstein revolutionizing space and time with relativity, Hubble discovering the expanding universe, the Big Bang, dark matter, dark energy.
All the way to this current frontier. Trying to reconcile gravity and quantum mechanics, dealing with singularities, maybe extra dimensions. It's quite a journey.
It really is. And it leads to perhaps the most profound concept discussed in the source material coming out of the quest for quantum gravity. It addresses that initial Big Bang singularity problem where GR failed.
What's that?
It's sometimes called the no-boundary proposal, championed by Hawking and Hartle. The idea is that if you incorporate quantum effects into the beginning of the universe, the singularity might disappear.
Wow.
By treating time near the beginning as behaving like another dimension of space. So space-time itself might be finite in extent, but have no boundary, no edge, no singularity where the laws break down. Think of the surface of the Earth. It's finite, but it has no edge or starting point.
So a universe that is self-contained. Finite, but without a beginning or end in the traditional sense.
That's the mind-bending possibility quantum cosmology opens up. A universe that just governed by the laws of physics, but without a singular starting point or an external edge.
Which brings us right back to that ultimate question posed in the book, doesn't it? If the universe can be completely described by a unified theory, if it's self-contained with no boundary,
Then what role is there for a creator? As Hawking put it, what is it that breathes fire into the equations and makes a universe for them to describe?
It pushes the boundary between physics and philosophy.
Absolutely. If the universe is entirely governed by scientific law, did it need a creator to set it in motion? Or does the theory itself explain existence? It's perhaps the biggest question that emerges from this whole history.
And one that science alone might not be able to answer. Something for you, the listener, to ponder.
Definitely something to think about. Our picture of the universe has changed so dramatically, and the quest continues.